Hello everyone, welcome back to the channel. Today we'll be doing the episode 3 of creating a custom ray tracer in C++ and Unreal Engine. Today is also the day we'll be actually drawing some code or typing some code in Visual Studio, and the goal for today is to draw something to the screen or the viewport of the Unreal editor. So with that said, let's get right into it. So the first thing you want to do is obviously create a Unreal project, and when you do that, make sure you have C++ turned on rather than Blueprint. And once you're inside the project, the first thing you want to do is, after the hot reload completes compiling, or not the hot reload, the live coding console, right? So when you open a project, you'll have a second console open called the live coding console. It's really annoying, so the first thing you want to do is go to editor preferences and go to live coding, and in enable live coding, uncheck it. So you don't want to use that. We could use hot reloads and Visual Studio compilations, or the build sequence inside Visual Studio, which is much more predictable. So once you have that turned off, come back to your content browser. You can create a new map if you want to, or create a or work with the default level. I recommend creating a new level, so come back to your content, create a new folder, name it maps, and then come here and right click, create a level. So it's just a blank canvas right now, and we'll draw something to this black area really soon. So once you have all that set up, come to your C++ classes and come back to your project folder, and then right click, create a new C++ class and choose actor. Now here's the thing, you could actually choose none. So that's the you could actually choose none, which is the empty C++ class with a default constructor. But for some reason in Unreal 5.2 or 5 and above, the none class doesn't show up in the editor. So it doesn't actually show up in the Unreal Engine reflection system. You need to put in the U class and U properties tags before the class initialization, which I found to be a little difficult, because even if you put the U class tag, it doesn't appear in the editor. You could still use it in Visual Studio, but it won't appear in the Unreal editor. So it's better to choose the default classes. So you have character, pawn, and actor. For our scenario, actor is going to be the best solution. So come back to next and name your actor anything you want, but we are going to follow proper naming conventions. So name it Ray Trace Manager. I'm going to hit cancel here because I have already set up a Ray Tracer Manager right here. So once your class compiles, you can just open it up and it'll open in Visual Studio. So forget that, forget you saw a function here. I was just trying to debug and check if everything was working. Okay, so we are officially inside a code editor. So what's the first thing we want to do when we're creating a ray tracer, right? Let's think about this. What is the goal of a ray tracer? Well, we just simply want to draw pixels to the screen, right? That's our primary goal. Now, there are multiple ways you could draw pixels to the screen. You could do it through shaders, compute shaders. You could actually draw textures to the screen using materials. And that's what we'll be doing in this series, right? We'll take a material, draw a texture in runtime, and the texture is going to hold pixel values calculated during the ray trace call, right? So the first thing you want to do actually is create a viewport. Now remember, if you haven't watched the previous episode, when we go into theory, I said we shoot rays through camera, right? We actually don't shoot rays through the camera. We have a camera point, so that, let's say this is a camera point and we have a viewport. So if I turn the camera, this is the viewport display. So in our case, it's going to be landscape. So this is the camera. As it turns and moves, the viewport is going to be here, and we don't actually shoot the light rays through the camera itself. So we have a starting point. The light rays are going to originate. So the origins of the light rays are going to be at the center of the camera object, right? So this is going to be the start point of the light ray itself, but the light ray is going to actually pass through the pixel positions of the viewport. And I'm explaining it with my hand here, but if I can, I'll draw some diagrams and put it up on the screen as I explain. I think the editor me can do it. So that's the point. We need to calculate the viewport first. So let's do that. Let's come into our header file of a ray tracer, and please ignore the demo class and the demo class edge. You don't require it. It was just a testing class for me. I was just making sure the code was running fine. So let's come back to our ray tracer hedge, and let's create another public and declare a variable. So let's uProperty this. So uProperty is pretty much a Unreal reflection system thing. If you don't put it, you won't find it anywhere inside the editor. If you put this, you'll find it inside the editor. So that's what I was saying about the none class. You need to actually declare this tag here, uClass, if you have an empty C++ class. But even though you have it, it has some bugs there. It really doesn't show up and it crashes all the time. So it's better to use actor, right? So I'm getting off track here. Let's actually make it quick and define a width, right? And I'm going to make it 300 for now. Now throughout the series, when we're debugging code or testing code, we'll actually set the resolution to very low amounts because we're running this on a CPU and it takes quite some time to render big resolutions. And also we need a uProperty type again to define. Have my insert on? Yeah. A float aspect ratio, right? So we have a width and aspect ratio. One more thing I want to point out is we are using Unreal Engine's naming convention. So it's Pascal case. So every first letter of a word is going to be capitalized. So we have width capitalized and aspect ratio capitalized. You could follow any naming convention you like, but just to be cohesive with the rest of the ecosystem, we are trying to make it as clean as possible, right? Let's also come down to private and define an integer called height. We don't have to define height here, but this is for scalability, as you'll see in just a moment when we come to writing functions. And let's come back to our CPP. I forgot one more thing. We have to come down here. Let's create another private. Again, another tip is you don't have to create separate privates and public. You could put this here, or just need one private tag, but I'm trying to like separate it based on what they do for our program, right? It's just making it cleaner, right? So let's create a function and I'll call it initialize. So this is actually going to handle our so right click and create declaration. This function is actually going to handle our viewport definitions, or defining our viewport, or preparing our viewport, initializing our viewport. So the first thing obviously we need to do is get the height value, because we haven't we haven't really defined the height value. So we'll define the height value by getting we'll cast it to an integer. and divide the width by aspect ratio. And just to make sure, we'll do a ternary operator. So we'll check height is less than 1, then so this pretty much just says check if height is less than 1, and if it is less than 1, then height equal to 1, right? Because we don't want height to be less than 0, then there's no point, we can't see anything. So once that's done, the next step is, let's think about it again. Okay, we have the width and the height of the viewport, but we have nothing else inside the viewport. The computer doesn't know what the viewport is actually right now. So we have to define a couple of different values now. So first thing we want to define is a focal length. And for the focal length, we actually need to define the look from point and the look at point. So, okay, my hand here, this is going to be the viewport, so I'm not going to use this again. So look from point is it's self-explanatory, the point through which you look at, right? So my eyes right now is the look from point, and the look at point is what I'm looking at. So the camera right now I'm looking at, that's the look at point. So to get the look at point and the look from point, we actually need access to a camera. So let's go back to our ray trace header file, and in the public section I'm going to create another public. Again, you really don't have to do this, you can actually use the same public statement, but we're going to actually instance a type called a actor, and it's going to be a pointer to a camera actor, right? So now what this does, the U property, I'm actually going to show you. I'm going to build it. So Shift Control B will build the file, compile the file, and you'll hear a sound in Unreal Engine. So you can see hot reload completed. And if I actually come to a quantum browser and come back to content, we'll right click, new folder, and then we call it blueprints. Double click the blueprints, right click, and blueprint class, and we'll get the class of our class that we just created. So it's ray tracer right there. So let's just name it ray trace manager. So what happens is when you drag this blueprint into the world, you can see we have a couple of options here. So we have the width and the aspect ratio. So we can also see we have a reference for a camera actor. So let's quickly do that. Let's come and create a camera and click the camera actor, and we can just come back to our ray trace manager, click the drop down and choose our camera actor, and quickly save everything. And then let's come back to our programming side of things. So we have the A actor, the camera reference. So let's come back to our CPP, and then let's define a couple of values here. So first we need to define a look from point. So that's going to be a F vector, and let's say look from. Or before that, I actually have to get the instance of the camera itself. So I forgot to do that. So let's come here and get the instance of the camera. We have the camera component. I'm sorry, we need the camera component, not the camera instance. To do that, we need to include a header file, include camera component. Okay, so, whoa, just give me a second. Camera, let's go in there, and camera component.h. Okay, so camera/camera component.h. We need to do that so we can access the camera component. So let's create a new camera component, camera component. It's going to be a pointer and we'll call this camera component, and we'll equal that to our camera actor dot get component by class, and then we'll just give camera component, right? So now we have the camera component from within the camera actor class. Now it's pretty much about getting the look from and look at point. So look from is basically the camera actor dot get actor location. So that's pretty much it. It's a method call. So f vector look at. So look at point is actually not going to be the camera actor's location, but rather the camera component's forward vector into a certain value. So let's think about this way, right? So I'm looking at something right now. So if I look straight, that point is going to be the look at point. So how do I calculate that point just with the position of my eyeballs? So you can take the position of my eyeballs, sorry, you can take the position of my eyeballs and the direction my eyeballs are looking at multiplied by a certain value. So that will get me the point that my eyeballs are looking at. So we can do the same thing here. Camera, so we can say look from, so that's the point we're looking from, so my eyeballs, plus, we can give a plus value, and now we need the direction. So you might be tempted to use the forward vector of the camera actor, but camera actor is not the camera component. So if the camera actor moves and the camera component doesn't move, the forward vector is going to get messed up. So let's actually instance the, or not instance, let's access the forward vector from our camera component. So camera component, and we can just say forward vector, and multiplied. For the sake of this video, we're actually going to use an int max value, so int 16 max. So it's going to be really far in the direction the camera is pointing at. So that's going to be a look at point. So we have a look from and look at points. Now it's time to calculate the focal length, theta, and the viewport height and width. So forget what I said about focal length and theta. We need focal length, theta, and h to calculate the viewport height and width, right? Now you might be asking, what is the viewport height? How is it different from the height and width we defined? Well, the height and width we defined are the image width and height, not the viewport width and height. So let's get the viewport width and height. So we need to do that by actually getting some other values, right? So let's actually put auto here, auto focal length equal to, focal length is pretty simple. We just look from minus look at dot length, right? So this is going to be a focal length, and next we need to calculate theta, which is the angle. So theta is actually going to be fmath degrees to radians and FOV. So we haven't really defined FOV, the field of view. So let's come back to our ray tracer and come back to a U property here, because this is something you could actually manipulate. And we'll just come here and do FOV, and we'll give it 59 for now, right? So now we will have an FOV, and then at last we need to calculate H. Now here's something about the naming conventions. This H obviously should be a small h, but then we'll be breaking Unreal's naming convention system. So I'm gonna actually keep it capitalized for now, but do keep in mind this is a small variable, or lowercase usually. So we have h, and h is tan theta by 2, right? Tan theta over 2. Okay, I don't know why I have my insert on. Okay, okay, theta, right? So this is what we require to get the viewport width and height. So let's actually create do it in auto again. So viewport height, we'll calculate the viewport height by 2 into focal length into edge. So that's our height, and we'll come back and say viewport width is equal to viewport height multiplied by static cast float, and come here and say width divided by height. So now we have the viewport width and height. Now remember, all might seem a little complicated, and it might seem unnecessary, but it's kind of not important. That's what I'm trying to say here. We can calculate viewport height the same way in every application. It doesn't matter. So the goal of the series is to teach you ray tracing, not about setting up your viewport. But if you do have any questions about setting a viewport up, do let me know in the comments below. So next thing we want to do is actually get a couple of pixel positions. So as I said, we are actually shooting light rays through the pixel centers of the viewport, not actually through the center of the camera. We're actually spreading it out through each pixel center of the viewport. So that's what we're doing today, or now, actually getting the horizontal and vertical vectors of our viewport and also the pixel location. So we need the first pixel location and the pixel delta u and v, so we can actually scroll across the viewport in pixel increments, right? I don't know if that makes sense. So let's say you're in a for loop, right? You increment by a certain digit. So if you have for int I is equal to 1 and I is less than a certain value, and then I plus plus. So I plus plus actually increments by 1. Let's say you do that same for a viewport, but rather than I plus plus being 1, you actually increment by the pixel delta u, right? So the amount of change per pixel. So we need to calculate the pixel position first and then the pixel delta u, so we can increment it by that vector. So keep that in mind. It might seem a little complicated, but it is kind of abstract. It's not complicated. So let's come and let's actually define certain values here. So first we need a f vector, the up vector, camera component dot so we get the up vector of the camera component. So the up vector of the camera is pointing in this way. So I'm the camera, like imagine I'm the camera, so my eyeballs is the camera, the up vector is going to be pointing up, right? So with that said, let's actually define a couple of other vectors. So u, w, u, and v. And let's start defining them one by one. So w is actually going to be the forward vector, right? So it's pretty much the same as saying look from minus look at. So let's do that quickly. Look from minus look at dot get safe normal. So get safe normal is the normalized function in Unreal we have, so we're going to play with that for now. And let's get the u. U is the right vector, so if I'm pointing here, it's going to be pointing in this direction, so the right vector. So let's actually get the u vector by actually doing the up vector dot cross product will cross with W, and then also get the safe normal. You don't really have to understand what the math does here. To be honest, I also don't understand, but you just have to know what values does what and what they represent in the system, right? So let's come back to V. So the V is going to be, I think it's W cross U. I'm not sure. Cross product on get safe normal. So let me quickly verify this with my previous project. Yeah. So once we have now, again, this might be a little confusing. The W and V are not actually the vector directions of the camera itself, but rather the viewport. So let's say I have a camera here. I said this is a viewport, so wherever the camera moves, the viewport also moves. So we're actually calculating the vectors of the viewport, not the camera, right? So that's why we do all this fancy cross product math here. So next, actually, I said we need to calculate the viewport delta U and V's. For delta U, that is actually going to be viewport width multiplied by minus U, and a vector viewport delta V is equal to be viewport viewport height multiplied by minus V. We're taking the minus here because Unreal by default flips it. So we have some problem in the coordinate system in the program we're writing. I haven't really debugged that. So we're gonna fly with this, right? We're gonna just flip the U value, and I think the U value has to do with the up vector actually pointing down. But I think just flipping it here into a negative value does a fine job. So let's actually stick with that for now. So once we calculate the viewport delta U and delta V, next we need to calculate the pixel delta V and pixel delta U, right? So f vector pixel delta U, which is actually going to be pixel viewport delta U, I think, delta U divided by the width of the image, viewport delta U divided by width. So this is actually the increment we're talking about in the horizontal and vertical axes. So when you think about it, we're taking the viewport and dividing it by the width. So dividing it, and we'll get that point, and that's going to be the increment value for each pixel in the horizontal and vertical axes. So let's actually follow along and get the pixel delta V. I'm actually staring at my phone, checking on my phone really, because I have limited storage space and have a limited recording time as well. So trying to be as quick as possible here, but also as clean as possible. So we have U and V. The last thing I said, we need to calculate the first position, so the first index. So let's say we're doing a for loop again, we'll have int I, and we need to understand what that int I is located at, or int 0 is located at for the pixel position, right? So let's actually get that. We'll actually define a f vector again, viewport upper left, and that will be focal length, not focal length actually, it's actually look from, so looking from the point minus focal length times W. So this is a forward vector multiplied by focal length. So focal length we have it calculated here. So it's just the amount of distance between 2 points, right? Focal length, and minus 2 divided by pixel delta U minus 2 divided by pixel delta V. not the pixel delta actually. I think it's the viewport delta U. So sorry, that's my mistake. So we have a problem here. What's the problem? Ternary operator does not match the argument. I think I might have found the problem. I don't know. Divided by 2. So, yep, so my mistake, guys, is actually divided by 2 rather than -2. So keep that in mind. I tried changing this into auto, but yeah, this was the problem. The last things last, we need to actually get the position of the pixel. So we're going to name this pixel location 0, 0. So 0, 0 self-explanatory, x and y 0, 0. So index number 0, right? So let's keep that in mind. And this is actually pretty easy. We can actually say viewport upper left plus 0.5 into, and then we need a pixel delta u plus pixel delta w, right? So yeah, so pixel delta u plus pixel delta v, and this officially completes our initialization function. So we have values here that we can use in setting up our first image. So with that said, let's get into setting up our first image. I don't have much time left, so but let's get into it, right? So let's come back to our ray tracer, and one thing let's do is let's build this first. So shift control B. This is actually a debugging practice. Once you have finished making a code block, you try to compile it and check if you have any errors, right? So then you can catch errors early on. So we don't have any errors, so that's a good thing. Just making sure everything is in line. And yes, it is. So let's come back to our private function in a header file and create a render function. So this is actually going to deal with rendering the image to the screen. So let's create that declaration here. So before we actually get into writing the entire render function, we need to actually define or create certain things in the Unreal world itself. So let's come to the Unreal world and let's come to content browser, and we have a materials folder, and you might not have it because I've created this prior to making the series just to test things out. So right click a folder and name it materials, right? So I'm going to delete it. Go inside your materials, and again you have a material here. You might not have it because I actually tested this out prior to creating the series. So right click material, and we're going to name this M post process. So let's just name it something render post process, right? So this material, so once you create a material, double click on it and come to the materials tab here, and the material domain, you actually want to change it to post process. So remember I said that we'll be writing textures to the screen of the viewport of Unreal Engine, but we'll be doing that by assigning textures to a material first. So this material is actually going to be the one that will be taking in the texture input and then displaying it on the screen. Now why we use post-process material is actually, post-process actually is the last call in the render pipeline. So after everything is rendered, the post-process is called, and the output of the image will be just slagged on top of everything else. The good point of that, the advantage of that is actually you can come down to your post-process actor and you can control the values, like if you want to display that material or not. So you can actually see the before and after your ray tracing, right? So keep that in mind. So let's come back to this, create a post process, and Now we have an empty material graph here. That's fine. Let's right click and create a parameter. So create a texture sample parameter 2D and name it render texture, right? So this parameter is where we'll be assigning our runtime texture. So we'll be calculating textures in runtime. So that will be our ray tracing calculation, and then assigning the value to the emissive function in runtime, right? Or rather to the material instance. We'll get in that later, but just keep that in mind. Make sure you have all this set up. So we need to have the material set up, otherwise we won't work it. In the parameters, you'll have a render texture in the global parameter. So let's close this again, and let's create a post process volume, and let's right click, create that, and this is where we'll be assigning the materials. So post process materials here, and we'll be doing it in runtime. We don't have to worry about this now. The only one thing I wanted to do was create a material and create a post process volume in the world. So let's come back to our ray tracer and get the instance or the reference to the post process material. So that's why I have a separate public statement here. We can actually a actor, or rather we need to come down here, include post process components, post process volume, post process component generator hedge. I don't think this is the one we need. Let me be okay. So we actually have to go to engine dash post volume. So make sure you have this included, this tag, header tag, and then we can come down here. Instead of a tag, we can actually put a post process volume. So post process volume, and we can actually call this post volume, right? And then that's pretty much it. That's all we have to do. Also, we need the instance or reference to our material. So I forgot that almost. You property, not the capitalized. Okay, property, and we need a material. So u material, a pointer, and then we call it to my material, right? So this is actually gonna take the reference to the post process material we just created, so we can actually assign the texture in real time. So enough talking, we'll build it and check if we have any errors. So we have no errors, so let's go and create our render function. So that's actually in the render function, the first thing we want to do is call the initializer. Now how this works is the flow statement here, right? So how the program flows is we'll actually call the render function in the begin place. So when the entry point of the program, we'll have the render function, and the render function is actually going to call the initialize. Now something you might have noticed is this is actually going to be a single frame render. So we'll only render one frame of the viewport. We won't be doing a real-time render. You could actually scale this up to be a real-time render, but I would recommend you port all this into the GPU. If you want to do that, you'll actually call the initialize in the begin play and then the render in the tick function, right? So with that said, let's actually get into displaying our first image on the screen. So let's come down to initialize and write a couple of statements here. The first thing we want is to create a texture, right? Pretty explanatory. U texture 2D pointer, just call this render target, not texture, because we already have a render texture, is equal to u texture 2D double that create transient, and we'll give the width and height. So this is why I declared the height in the global context. And let's actually come and say render target, add to root, and render target, update resource, right? Okay. So with that said, the next thing we want is to manipulate the values inside the texture, and we can't actually directly do that in some applications. The first natural instinct is going to be render target and just accessing the index of the pixel. So it will be bracket, square bracket, 0, 0, and assigning a color value, but it doesn't work that way. We actually need to access the MIP maps. That will be the scaled down version of a texture pretty much. So let's actually create a, I think it's an F texture, I don't know, F texture 2D MIP maps. Yeah, there you go. And this is going to be, and let's actually call this MIPs or MIP, right? And now we need to get the MIPs from the render target. So render target, and we'll get the platform data and get the MIPs from it. And MIP 0 basically means the highest quality of a texture. So indexed as 0 is going to be highest to lowest. And then we'll come and create a void pointer texture data. So this is actually the one we'll be manipulating. We'll call this MIP and bulk data dot lock. We'll say lock read write, right? So we can read and write from the texture data. So the next thing we want to do is write a for loop. So int I is equal to, let's actually do it from j. J is less than width. J is actually the height. So height and j plus plus. And another for instance. So let's go for int I is equal to 0. I is less than width now, and I. You actually don't have to follow this. The I and j convention, you can put it I then j, which is more common. Then once we're here, this loop is actually where we're going to add color values, right? So let's actually create a UV coordinates. So we can do that by saying we'll actually do a auto. So auto R, and we'll actually do the double of j, double of I actually, divided by width. I think we might have an error here for the static casting, but if we do, we can actually come and change it quickly. And double of j, and we'll call that height. I think j is the width and I is the height. Let's just follow along. And the b is going to be a 0, so we don't have to worry about that. Now the problem here is we'll actually see a black screen if we actually render this color values, because we're actually clamping it down, or the real range is between 0 and 1, and the color range is actually between 0 and 255. So this is going to be always black, so we need to cast it to an integer range of 255. So we can do that actually by saying r is equal to static cast, we'll say integer, and then we can say 255 multiplied by r, and we can do the same thing for g and b. G and b, we can say g and GNB, right? So now the point has come where we need to write the colors to the texture data. So it's kind of a tricky syntax actually. We had a pointer or just asterisk at this point, and we actually call the f color pointer again, and gonna call texture data. So that's what we have defined, accessing the map values, plus I plus j into width, and that is actually going to be pixel color, and we'll define the pixel color here. So f color, right, it's going to be color value, color, can I do a pointer here, pixel color, and then we can just put R, G, and B. Okay, so we can't actually do this. Double cannot be initialized. Type color. We did actually, okay, I think this could be the problem. I'm not sure. Is casting okay? Oh, okay. I think that's fine. Let's keep IR and IG and IB for now. So we have pretty much written the new color values to a texture, right? So now it's all about assigning that texture to the material and displaying it in the post-process volume. So let's do that. Let's actually compile and check if we have any errors. So we actually don't, but we won't know until we run the program for logical errors actually. So now we need to create first we need actually to close the MIPs. So MIP dot bulk data dot unlock and update the resource. So render target and update resource, and once that's done, now it's time to create our material instance. So material dynamic instance, I guess, dynamic instance dynamic, a pointer, and I'm going to call this material instance, and then I'm going to actually come down here and say view material instance again, dynamic create. We're going to call the first reference to the material, so it's actually going to be my material, right? Okay, my material, this one and this, right? So that's that, and we're actually going to assign the texture value to the parameter of the material itself. So we can do that by saying material instance set texture parameter value, and we'll call an f name, and we actually named it render texture. So render texture, and then we can actually give the value. So it's actually going to be the render target. Okay, so now we have that done, but we're not done yet. We need to actually create a blendable object. So blendable, so blendable not blendable interface. So I think I'm missing something. Let me quickly so it's actually called f weighted blendables, sorry. So f weighted blendable, I'm going to call it new blendable, and then just leave it there, and new blendable. We're going to assign the object, so dot object is equal to material instance there, and new blendable the weight of the blendable, right? So by now you might have realized this is actually corresponding to the post-process material. We need to do all this to get there. So I'm actually going to give a weight of 1. So that's right. And the next thing we want to do is actually create another class. It's called the script interface, I guess. Script interface of iBlend interface. And I'm going to call this blend interface and blend interface dot rather blend interface dot set object is going to be the new blendable dot object, I guess. Yeah, so dot object, and then we need to actually cast the next thing interface. So set interface, and we'll actually static cast to type iBlendable interface. We'll actually cast the new blendable object to that, and this should work. iBlendable interface. Cast. So okay, so that works. And the last step is obviously taking the new interface and putting it inside the post-process volume. So we have the reference to a volume, so we'll just say post volume dot add or update blendable, and then we can just give our new blend interface. So that's pretty much it. So let's do it for one last time, build it up, and let's see if you have any errors or the logical errors. So that's that. Let's minimize, come back to Unreal Engine. Let's see if you have Ray Trace Manager and everything set up. So pros plus volume, let's assign the value. My material, let's assign that as well. So m render post process and width and height and everything. So let's actually save everything before we run, because when it crashes, it's going to be bad. So let's run. So we actually have a black screen rather than anything. So let's come back and check what we're doing wrong. Wi-Fi width and height. J is the height, width, ij into width, pixel color. So the black screen is actually a result of two silly bugs or human error actually. So the first thing is we need to go to our post-process volume and search for infinite extent and infinite extent unbound. Make sure you turn it on, and then come to your code, and we haven't actually called the function anywhere. So the program enters the loop or the code, and we don't have any render calls here. So let's just call the render call here at the beginning. So let's just call render. So it's pretty much a silly mistake, and let's build it again. Now we should see some images, right? So let's minimize this, and hopefully we have a UV coordinates on our screen. So this is how we'll be writing textures to the screen in Unreal Engine. But obviously we'll be doing ray calculations, and if it hits something, we'll get a color to that, scatter directions and stuff like that. But for now, this is pretty much it. This is the first step in building a ray tracer. So what you can actually do is come to a post-process volume, okay, and come to the material section, and you have the array here. We have the weight of the array, so we can actually put it at 0 and see what happens without the render active, right? So that's the cool thing about this. We can actually turn on and off our ray tracer when we need it to check before and after pictures, right? So that's pretty much it for the first episode, or the third episode actually, but the first programming episode. We've actually got something going on. We have written textures to the screen in Unreal Engine. And the next episode will actually define our first material. So it's going to be a diffuse material, and actually writing our first, or drawing our first actual ray traced image to the screen. So with that said, I will see you guys in the next episode. Bye bye.